Thank you for the introduction. Good morning, everyone. I'm going to present a talk on capacitive micromachined ultrasound transducers for in vivo imaging. Cardiovascular diseases, which is diseases to your blood system around your heart, is a major cause of deaths on a global basis. Plaque buildup in your blood vessels, mainly due to your habits with bad cholesterol, will normally be encapsulated by a fibrous cap by the body. But if this, in case of an inflammation, this cap will rupture, will leave blood clots and lead to an infarction. So the doctor can put in a stent if you have a when you have a situation like this, the doctor can put in a stent for you, but finding the correct spots to treat is a bit difficult. And distinguishing the vulnerable plaque from the stable plaque is challenging with the current ultrasound probes available. You would need an ultrasound probe on a catheter needle to go into your blood vessels to distinguish the different types of plaque. So the traditionally PCT arrays that is used for ultrasound probes don't have the desired resolution. CMUTs, on the other hand, might provide a resolution and the frequency range that we need, and it also have the possibility of 3D imaging capabilities. Another application we've been targeting is characteristic of colon cancer by a robot pill. The pill shown up here was developed in an EU project called Vector. Unfortunately, we weren't in time for the prototype, so the pill was the prototype was made without our CMUT sensor. But we believe that the application is quite good for, and the CMUT is quite good for this type of application. At the moment, we are working with a company called Medistim to make ultrasound probe that is used during an operation as a quality control for the doctor mostly while doing bypass operation. You can monitor the flow of the blood vessels, so just to that the doctor can check that he has done the work that he should do. So I'll just go briefly through what a CMUT actually is. The conventional ultrasound probes are linear arrays of bulk PCTs and slabs of PCT and matching material. So because of limitations in the processing capabilities, it's challenging to produce probes with a high frequency to get the needed resolution that we need here, and also they are linear arrays, so you cannot make a 2D structure with a typical way of doing this, and that means that you can't do 3D imaging and beam steering where you want to put a phase delay on one side or the other to control the beam. And a wider frequency band is also desirable. So here's where the CMUT comes in. A CMUT is actually basically a drum that is actuated by electrostatic forces. So you need some kind of an suspended membrane, preferably with a sealed cavity if it's to be used outside of air. And you also need, of course, the electrodes for activation. And you can choose here for MEMS fabrication with bulk and surface micromachining. We believe that the bulk micromachining, at least for these frequencies, is the best because you get better. You can use high quality materials and you get better material properties. Just a principal view of where you have the metal electrode. This is the simplest simplest CMUT you can make, a metal electrode on top of a suspended membrane, and you just use the silicon substrate as the ground, and you make a DC bias to control there some pre-moving of the membrane, and then the AC to transmit, and then you receive, you collect the signal in reception mode. If you want to do 3D imaging, and you need and also for the beam steering, you would need a bit more advanced device, because you would like to have groups or single elements or groups of elements connected together so that you can control them separately. So we have a frequency requirement from the application and the typical view. For this blood imaging within the blood vessel, you will need a frequency to 30 to 60 megahertz to get, we believe, to be able to detect the plaque that we are looking for. Imagine putting this into your blood vessel. You would like to have the front plane grounded, means that you cannot have the electrodes on the front side. You will need some vias so that you can control the elements from the back side. This is the device that we have proposed. We have chosen bulk micromachining with the transfer of layers with wafer bonding, and we have been within the project. I'm not going to go through this in the talk, but we have been through the proposed a design where we have the vias from each element going down, and you will have some 3D stacking device, and first a low voltage receiver electronics that must be close to the CMUT because of the voltage. You have some high voltage transmit electronics under there, and to at least for what is called the intravascular ultrasound within the blood vessel, you will need a signal processing and communication layer on the bottom, simply because you cannot, if you have seen an ultrasound probe, the cables are this thick, you cannot take that out of your blood vessel. So you need some signal processing and communication treatment also on the chip to lower the number of cables out. So for those interested, you can go further and look at these references here. The modeling for the device you have made here is also discussed elsewhere, but I will just go through it. We have calculated the single CMUT acoustic modes. Then we have done some static analysis to find the DC bias, and then the lumped parameters for each DC bias is found, and then we have made a dynamic model of a 2D array in fluid. So to reach the frequency and dimensions needed, you have found these parameters here: membrane radius of 5.7 micrometer, together with these two different membrane stacks. Was what we found to the correct frequency. We have connected 2 by 2 elements together, so that the single element, or the cavity pitch, is 12.5 micron. So 2 by 2 elements is connected together to create a via pitch of 25 micron. And we have made a cavity, the depth here, to 60 nanometers. This is you need to do some DC biasing, so it decides how far you can go down, and it also limits how much movement, total movement and power you can get out. But if you have too high cavity, you need a high voltage to activate it. So I'll just guide you through the processing and just show first how this is the simple design of one element. Is the 2 by 2 membranes and the polysilicon, the via, and the triple stack membrane. So we start with a 2-layer or 2-mask reactive ion etch process to create the bottom electrodes and the vias. And we grow isolating oxide and fill them with polysilicon. And the polysilicon is doped. Then we do a CMP process to get a smooth surface, and we do the cavity etch of 60 nanometers, and then we etch down the isolating oxide to change the properties a bit. Then we deposit LPCVD nitride, that is to be the membrane, on a different wafer. We bond the two wafers with fusion bonding, high temperature anneal process, and then this is the bonding step, and then we etch back to reach the vias. So the oxide is not shown there, but then we have an isolating, grow up a new isolating oxide, pattern the aluminium on the backside, and then we do the cavity etch on the front side to reach the membrane. So at this stage, the thickness of this area is approximately 25 microns. Then we deposit the rest of the membrane stack, the aluminium and PECVD nitride. So two SEM pictures from the processing. This is the wafer at the stage before bonding. You can see the 2x2 elements. You can imagine that this is a bit lower than here. It's not easy. It's 60 nanometer height difference, and this is I think it's only the isolating oxide. I don't think we reached the middle of this is the via. It's polysilicon filled. And you can see here, not very sharp, but you can see how this is the isolating oxide, and you have crystalline silicon for the bond interface. This is the membrane stack after wafer bonding. You can see the gap, the polysilicon electrodes, and isolating oxide. So the measurements, we have done a measurement of pull-in and snapback behavior to find the pull-in voltage. We have done measurements at different DC bias. We didn't quite get the resonance frequency to correspond with the simulations. We believe it's because we haven't met the correct, or by changing the material parameters, we got a quite good match, but that was after the fabrication. Okay, since I'm just focused on this one, this is the measurements in rapeseed oil. It has pretty much the same acoustic properties as blood, so that's why we have chosen that. We reached 12 megahertz resonance, which is a bit lower than we wanted, but we still think it's possible. We know what to do to get that better. So quick summary. I think we have a unique process because we have the small pitch. It's one of the highest frequencies with wafer bonded membrane, and we think that we can, and the device is ready for 3D packaging, and I think we are exploring this further to get to a good working device for the application. Okay, thank you.